Hello. So we are going to continue chapter 6 about normal distribution today. In the last lecture was about an introduction to continuous random variables. The idea was that the continuous random variable has a very different characteristics from the discrete random variable we considered earlier. So the main idea is that a continuous random variable has uncountably many infinite number of possible outcomes. Therefore, we cannot list all the possible outcomes and we cannot consider probability assigned to each of the outcomes. So we had to introduce a different approach to describe the probability distribution. That is, there are two different ways to describe the probability distribution of a continuous random variable. One is using the cumulative distribution. So we call the function that assigns a value to its cumulative probability as the cumulative distribution function. And its acronym is CDF. So usually I'll call this CDF and denote it as capital letter F. And the other approach to describe the probability is based on the probability density function, which is abbreviated to PDF. A probability density function is it connects the probability to integration. So inside it's the integrated. So f, lowercase f is the density, and then given the density, the probability can be represented as an integration, right? So these two different approaches are equally important. Both are important, and they have like pros and cons. When one is better than the other in some cases. So I'm going to show you how we can utilize them in the normal distribution case. So far the discussion was just was general. It was for generic continuous random variable. But from now on, we are going to start to focus on the normal distribution. And it is, as I said, it's really important, the most important distribution in any field of study, any field of studies. So like social sciences, natural sciences, of course, mathematics, statistics, whatever, the normal distribution is the basis, right? So, for example, in natural sciences, what's interesting here is the distribution you observe in the nature follows normal distribution. So, for example, heights and weights of animals and plants are like approximately normally distributed, which is very interesting. And velocities of the molecules in the ideal gas, actually I don't know what exactly it means, but it's like, how particles move in the ideal, like maybe situation. And then the velocities follow normal distribution. Maybe if you have heard about Brownian motion, then Brownian motion is based on the normal distribution, right? That's what I'm talking about, but I don't know what that is. Anyhow, I just wanted to say that the normal distribution can be found anywhere, like anywhere in natural science, of course, but also in social sciences. The normal distribution is very commonly applied to many examples. For example, when you have a test score, we usually standardize the test scores and assume that the distribution is normal, which is usual t-test, t-score, or t-standardized scores, which is commonly used like when you measure the IQ. IQ is based on the normal distribution. And Black-Scholes equation in finance. If you are seriously interested in finance, you may have heard about this equation. These two guys are economists who already got won Nobel Prizes decades ago. So this equation is to calculate the appropriate price for option, like financial option products, right? For example, like, so they assume that the price distribution in the future is normal. Then under that normal distribution assumption, you can calculate how much the financial asset is worth. Like, so that's this equation, and they got Nobel Prize thanks to this equation. And Six Sigma, if you have heard about Six Sigma, it is in management, so it's about quality control. So in manufacturing, there are always manufacturing errors, but how to minimize that, how much you have to minimize that error. It's in the prime time of General Electronics, GE, which is in our town. Six Sigma was their principle that made them famous. So they try to make the error less than 6 sigma distribution. So the 6 sigma is also based on the normal distribution assumption. So anyhow, these important and famous theories are using the normal distribution in social sciences. So what is the normal distribution? The normal distribution has two parameters. So by the way, the normal distribution does not have a direct experiment that implies the normal distribution, like binomial distribution. So when I introduced the binomial distribution, I described how to design an experiment so that their outcome follows a binomial distribution. But now, for a normal distribution, it is purely theoretical, hypothetical experiment, or it can be understood as a limit. So later, in the next chapter, you will see how the normal distribution can be obtained. But so in this chapter, I will not describe an experiment that corresponds to the normal distribution. There is no simple thing like that. There is no kind of real experiment that generates a normal distribution. Anyhow, so then how is the normal distribution defined? It is defined by two parameters. And kindly, the two parameters are mean and variance. So if you know the mean and the variance of the distribution, and then if it is normal distribution, then you know the full distribution of the random variable. So you can change those two parameters. If you change the values of the parameters, then you will generate different normal distribution. But of course, the variance parameter is restricted to be strictly positive, because variance cannot be negative. And if variance is zero is theoretically okay, but when variance is 0, that means there is no variation, so means nothing. So we restrict the variance parameter to be strictly positive. So anyhow, these two parameters fully describe a normal distribution. And then we write a random variable x follows normal mu comma sigma squared. By the way, this is called mu, Greek letter mu, and this is the Greek letter sigma. So sigma squared. So mu comma sigma squared is the parameter for normal distribution. Or simply, often we drop all the other, we only use the initial n. So normal distribution is so important, so commonly widely used, so we simplify like this. N stands for normal distribution in this context. Then, if you look at this graph, then you must be familiar with this kind of graph. This is the normal distribution. So the blue distribution is mu 0 sigma squared 1. And if you change mu to 1 from 0 to 1, the distribution will move to the right. So from blue to the orange. And then when mu changes to -1, then moves to the green. So moves to the green. By the way, you know this graph is the bell curve. Bell curve is the probability density function for a normal distribution. So remember, like I already introduced the bell curve here. So the area below the distribution, below the curve, is the probability. So this curve is the PDF, probability density function, for the normal distribution. So any normal distribution, no matter what the parameter values are, it is always bell-shaped, bell curve. And as you see, when you fix the sigma squared, when you fix the variance and change the mean, it shifts parallel. And here, now, let's think about changing the variance. So blue is again the standard, 0 and 1. If you increase the variance, then larger variance means more variability. The distribution is more spread out. So the bell curve looks like the orange, like this. It flattens. It becomes wider, flattens out. But when you lower the variance to 0.5, then smaller variance implies more concentrated distribution, less variability, less dispersion. So it's more concentrated at the center. So it looks like it's another bell, but it's a taller bell curve. So as you see, the variance determines the steepness, the angle of the how tall or how flat the bell is, and the mean mu determines the center. So the center, the peak, the center is determined by mu. But here, because you do not change the mean, it is always centered around 0. That's what you get. So, in summary, what you can learn from the PDF. From the bell curve, what you learn is, first, it's always symmetric. Always symmetric, right? Symmetric about the mean. So, that means it is symmetric about the mean. So, the probability below the mean is exactly 50%. Probability above the mean is always also 50%. So, the mean is 50 percentile, which is the median. So the median is the same as the mean. And also, because it's symmetric, it peaks at the mean. And so the mode is where the probability is highest. That is also the mean. So the mode, the median, and the mean are the same thing. So these three guys are measures of central location. So all of them are the same because of the symmetry. And the range is from negative infinity to the positive infinity. So range is infinity. By the way, even though it looks like the probability is 0 here, but actually the probability is really, really small, but not exactly 0. It never becomes 0, even if it goes even further than that. So it never gets to 0 to the infinity. And probability decreases. The probability is highest around the center, around the mean, and always the probability density decreases as you go away from the mean. That means the mean is most likely to happen, and the extreme guys, outliers, are always rare in normal distribution. And I explained this. Increase in the mean shifts the curve to the right, parallel shift. But increase in the variance is about the flat or tall widens. So this is what we know, what we learn briefly from the bell curve. That is the normal distribution. So I'm going to continue how to understand the normal distribution, especially how to calculate probabilities from the normal distribution. So I'll do that in the next video. See you later.